So just a few more slides to kind of finish up this intro to acids and bases. This is showing you weak acid providing a proton here. This HB provides a proton. It's picked up by the water molecule and it forms the hydronium cation. We talked about that. And the B minus is kind of like the, well, if you're going back the other way, the B minus is a proton acceptor, isn't it? So it's acting as a base, where it's an acid over there in the HB form. As the B minus, it's a base. So we do a lot with water. We do a lot with water as our matrix, okay? So in this case, water is acting as the proton acceptor. So in this case, it's acting as the base, okay? And that will be the case if the Ka for your weak acid is stronger than the Ka for water. And we'll be talking more about what the Ka for water looks like. Switching it up here, now we have some sort of weak base, okay? Actually attacking a water molecule to abscond on with one of the hydrogens, and it forms HB over here on the product side, and then what's left from the water molecule is the hydroxide ion. And so one of the things, a lot of times students will come into this class and they'll think, well, I know if you have excess H pluses, it's acidic, and I know if you have excess OH minuses, it's basic, and that is very true. And that's kind of what we're kind of hinting at right here, too. It's very true. And I guess I should put in the middle, as I've drawn this, starts with letter N, what do we call this? What's in the middle between acids and bases? Starts with letter N.
Neutral.
Yes. And I can never spell neutral, so we'll spell it like that today. So in neutral, actually, your H pluses are equal to your OH minuses. It's kind of fun, so kind of start to be thinking about that. By the way, very bad hair day. I'm not switching my hair, but okay, I erased it, but there is an International Space Station. You guys are familiar with that, right? Every 90 minutes, it orbits kind of from pole to pole, the Earth. So the International Space Station, there's a website out there where you know when it's going to transit the moon or the sun, but you have to be at the right location, so it's a long story. But tonight about 9:45 or so, if you're in this vicinity, not everywhere in Keokuk, but like literally around the campus, you look up at the moon, and I don't know which direction it's going to go, but I think it should go up and down like that. Basically, the ISS for 1.8 seconds is going to go in front of the moon.
So it orbits the Earth once every 3 hours?
90 minutes, so twice in 3 hours. Yeah, 90 minutes, so an hour and a half, an hour and a half.
I think it's got broken.
Yeah.
That's crazy.
Yeah, for sure. But these transits, it's called a transit, these transits are kind of rare. You have to chase them down. And so today I'm just staying. And so anyway, I loaded up all my gear. My little car is just full of a telescope and camera equipment and brought my French horn.
Like naked eye? Or?
I don't know. I would think so. I would think with binoculars you could. And it kind of reminds me of E.T., you know, where you have the, I go in front of them in the bike with E.T.
What time?
9:40, probably make sure you catch it, but I think it's more like 9:47.
Are you going to be at the school then?
Yeah, I'm going to be up here in the hill over here. I'm going to set my telescope. Yeah, so if you want to come see. I know.
Might be join you up there, bring a little picnic blanket.
Yeah, I brought a table because I think it's going to be kind of wet. So.
Well, that's cool. I might do
Now
that.
you ruined my picnic
Yeah.
idea.
So anyway, that's why my hair's like, because I was like loading up and I was like, oh, okay, that's what it's going to be. It's either stay home with that hair or go to school. So anyway, so KAs are, and I went ahead and kind of showed you over there kind of the Ka and the Kb. So Kas are associated with, we call that ionizing, a weak acid ionizing to form H plus and B minus. And I talked about I usually use the term hydrolysis. I usually say the B minus hydrolyzes a water molecule to form HB, accept a proton, form HB, and then release hydroxide ions. So those are the equilibrium statements, Ka and Kb. All right, so what else we got? All right, so these are just some terms, and actually the other day when I said that H2SO4, sulfuric acid, is a strong acid, And Olivia was like, well, does it kick off both of them or just one? And that is an example of what we call a polyprotic acid. So monoprotic just kicks off one proton. Polyprotic acid kicks off 2 or more protons. And it happens, totally happens.
Is there one that's more common than the other? Like, is the monoprotic, is that more common?
I would think more substances just have 1 proton to donate than something that has 2 protons to donate. Well, with phosphoric acid, it's H3PO4. So it's actually polyprotic with 3. And the way it goes, and we kind of saw this with the Kas, the first one to go, it ionizes a lot, and then less for the second one. It gets harder and harder to kick off one, so you're kind of adding less, the strength of those acids decrease. And then the last term, if somebody is like left-handed, right, is that ambidextrous? Ambidextrous, okay, good. Ambidextrous. So I kind of think of ambidextrous and amphipromotic, final answer, amphiprotic. Something that it can actually accept a proton or donate a proton. If it accepts a proton, it's acting like a base, and if it donates a proton, it's acting like an acid. And that totally happens too. And the most common substance that does that is water. Let's see if I have it up here. I guess I probably do have it up here. Water donating a proton as it goes from right to left, and water accepting a proton as it goes from left to right. It's amphiprotic, whatever that is. Okay, I think I did write that last time. Amphiprotic, ambidextrous. Okay. So again, we do a lot with having water as our matrix, but it wouldn't have to be. And this just kind of says the strongest acid that will exist in an aqueous solution would be the hydronium cation, which is the same thing as the hydrogen ion. Strongest base that will exist would be the hydroxide ion. And you guys already did these. Okay, so let's take a look at part 2. Yeah, I was thinking about part 2, and I'm real excited about this because I think some of you guys are numbers people, so we kind of get some numbers going on here, which is kind of fun. Well, why is it doing that? But the other thing is it deals with, we kind of blow off our weak acids and weak bases, and we're going to kind of talk about strong acids and strong bases just to get this going here. So I do that. Well, that's just crazy. And I do this. Oh, I know. I did that wrong. I got it. Okay. Okay, so pH, there's a lot of things. It's like, what's the pH of your deodorant, right? You guys told me that, we have citric acids over here. We kind of talked about bleaches would be over here. So we kind of have this thing called the pH scale. But you probably figure that the H part in pH is hydrogen, but I'm going to tell you the P part is something generic. It's a P function of the hydrogen ion. So think broader. So I'm going to broaden your scope here. pH has to do with the hydrogen ion, but P anything, and actually we're going to switch gears, and you saw it Friday that we have a column called pKa. Well, what do? Well, we took the log base 10 of the Kas times -1 to get the pKas. How do we get pOH? You take the OH, molar concentration, take the log of it, times -1, and that's your pOH. Okay, so how do we get these pHs? We took the log of the molar concentration of H+ ion times -1. So it's a P function. So yeah. So it's applying like a little a function, okay? It's like a little math problem. So the P of anything, right? So, and this homework is good. I think it's going to kind of pull you through to do it. Before we talk more, well, we'll be talking about working some problems. But let's just consider a water molecule breaking apart into H plus and OH minus. Looks balanced, makes sense. This is called the autoionization of a water molecule. Now we could write the equilibrium for that. It's products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. The H2O does not appear here. Okay? So now we have another K. Sorry. You're like, are you serious? So add this to your Ka, Kb, Kw. Kw is just for the autoionization of water. What is it? It's the molar concentration of hydrogen ion raised to the first power times molar concentration of hydroxide ion raised to the first power. And there is, let's see, if you want to put a little star on here, memorize, however you do that, you're going to want to memorize this value. You're going to want to memorize this. Now, I'll go ahead and warn you that sometimes when I work this, either in problems or like, in my lecture notes or on a test or something, sometimes I will round that coefficient to 3 sig figs, 1.01 times 10 to the minus 14th. So you'll just have to kind of bear with me. 3 sig figs, the coefficient's 1.01. 4 sig figs, the coefficient's 1.008. We talked about thermodynamic standard temperatures is 25 Celsius. So that's at 25 Celsius. It is temperature dependent. I have a slide coming up to show you the Kw at the different temperatures. All right. So we have solved, how do I say this? This is kind of fun. We have solved K expressions, KSP expressions. Well, if your water, if your water is neutral, I told you that this molar concentrations are equal. Well, if they're equal, then if you take, how do I say this? If you take, I wish I would have done this, watch this. 1.008 times 10 to the minus 14th. And if this is like x, they're equal, then if you take the square root of that, you get 1x. Does that make sense? Okay, good. Take the square root of 1.008 times 10 to the minus 14th, and you get 1.00 or whatever times 10 to the minus 7th, and that's the molarity of the individual ions when water has autoionized. Is that not fun or what? I think of this as, I'm going to call this a neutral solution. Can't spell neutral. Does that make sense? They're equal. All right. Cool. So let's see if this video works. It should. Give it some sound.
Substances. Two water molecules can interact with each other to produce a hydronium ion and a hydroxide ion by transfer of a proton from one water molecule to another. This process is called autoionization.
So and this is kind of a fun thing. So in neutral water, what did we just say? If it's at 25 degrees Celsius, you're like, is it acidic? Is it basic? Well, the molar concentrations are equal, but it does autoionize to a certain extent, and that's 1.00 times 10 to the minus 7th moles per liter. Does it, okay? That's like neutral water. Autoionization. Okay. So Kw, in this case, can you see where the thing that's different is instead of H plus, we've got H3O plus, which that's kind of everybody's problem to bear, that whenever you see H plus, it's basically interchangeable with this. Okay, interchangeable. This is just showing you the same thing. This is kind of fun. It kind of talks you through. I like it because one water molecule is being the proton donor, one water molecule is being the proton acceptor. I think that's kind of fun, of those two water molecules. So blue box, seems like we already said this. So KW, now this doesn't say for a neutral solution, does it? It just says for any dilute aqueous solution. So as we get rolling here, how do I say this? If you're dealing with an acidic solution, the molar concentration of the hydrogen ion times the molar concentration of hydroxide ion, if it's at 25 degrees Celsius, should be equal to 1.008 times 10 to the minus 14. And so if your H plus went up, guess what? Your OH minus went down. And that's exactly what happens. Okay, so let's talk pHs. All right. So this is where, and I don't know if you want to find, get your, you brought your calculator, I wish I would have warned you. And get it out. I brought my calculator. And I want to find your LOG key. I think it's on my desk. So this is where, if you know the hydrogen, the molar hope we're on the same page with this, any brackets means molar concentration. If you know the molar concentration of the hydrogen ion, you take the log of it times -1, and that will be your pH. So I've got some examples coming up. Well, if instead you're after the pOH, then you need to get the molar concentration of the hydroxide ion, take the log base 10 of it, times -1, and that will give you the pOH. Well, let's just say you don't have the hydrogen ion concentration, you have the pH. Well, if you have the pH, and you want the hydrogen ion concentration, you take 10 raised to the negative pH, and that will give your hydrogen ion concentration. And have a similar thing for the hydroxide ion down here. Sometimes I kind of show you how that works. Basically, in order to kind of get to the same relationship, you take 10 raised to the pH, and 10 raised to the log base 10 of a number is that number. That's how that works. So you can kind of convince yourself those are the same thing. But that's how you're going to work some problems. So we have the KW, which is the relationship in dilute solutions, neutral or at least dilute, acidic or basic. Molar concentration of the hydrogen ion and hydroxide ion is going to be that 1.008 times 10 to the minus 14. Okay, that's KW. Also, and you can convince yourself if you want to, but for any water solution, the pH plus the pOH will be equal to the pKW. Now here's where I wish I would have. Now if you have your calculators, try this. For this one, go ahead and take, let's see, how does that go? Take log base 10 of 1.008 times 10 to the minus 14th, okay, and see what you get.
So you always remember to multiply by -1, right?
Right, exactly, because you'll get a negative 14.00. Yep.
13.996.
Okay,
Yeah.
13.996? With 4 sig figs. Very good. So this actually is a nice little, and we're going to work some problems, but the pH for the same solution, the pOH for the same solution, you add them together, you should always get, at the temperature of 25 degrees Celsius, 14.00 when you add the pH plus the pOH. That's kind of fun. Cool.
And is that where we get like the scale from?
Yeah, that's how the scale kind of fits in, exactly. It maxes out at 14. I think I have a slide coming up that says you can have something more basic than pH of 14, but it kind of, that's generally how far it goes. Cool. Well, you guys just did this, right? Yeah. So kind of put another way, this seems like I'm just kind of repeating myself here. Okay, you guys see where this, and now I've gone just to 2 sig figs in the coefficient. 1.008 or 1.01 or 1.0, you're like, oh. And the rule of thumb is you never want a constant like this to be, to limit the number of significant figures you're allowed in your answer. So if you have terms that have 3 or 4 significant figures that you're working with, then you better go with a coefficient of kW that doesn't limit you.
Okay, so constants don't determine significant
You,
figures in general?
you want to avoid that. It depends on how you work your problem. You never want to round a constant like kW so that it's the driving factor for how you round. Do you know what I mean? Because you had options. Instead of going with 1.0, you could have gone with 1.008 times 10 to the minus 14. So you never want to let that be your short chain. All right. Okay. What do we think? So, practical pH runs from 0, I put 1 up here, but from 0 to 14, pH of 7 is neutral, okay? But you can have more pHs outside of that range. And we'll kind of be looking at that, I think, here at some point. So let's see what this video says. Oh, there's no sound to it. It's just kind of showing you the... One more time. Now that we know there's no sound. Go over here. So if you multiply those two together, you get 1 times 10 to the minus 14. That works. As 1 goes, in this case, the hydronium ion is decreasing, the hydroxide ion is increasing. Cool. What else we got? This is another way to look at it, okay? Sometimes these figures look almost too busy, but you can see the pH of 7. Notice that at pH 7, the pOH is up 7 because you add them together, you get 14, right?
So the more acidic, the lower the pH.
The more acidic, the lower the pH. Yep.
I always thought that was the opposite.
No, the more acidic, the lower the pH. But now we can actually add to this to kind of boggle our mind. And what's the pOH of something that has a pH of 1? Not 14, 13, because added together they equal 14. Do you know what I'm saying? Right, how about over here? What's the pOH over here? 0. Yep. See how that works? Yep. So you're like, oh, why do we need 2 scales? Well, I don't know the answer to that. But actually to work problems, sometimes you don't want the hydrogen ion concentration, you want the hydroxide ion concentration. And pOH is related to the hydroxide ion concentration, so.
Yeah, I've never even heard of a pOH. I always hear pH.
Right,
You know?
right. But they're kind of competing scales, yeah. They go backwards from each other. Yep. Yep.
One used more often than the other, it's kind of equal.
Well, I'm kind of like Olivia. I hear pH a lot more than I hear pOH. I really don't.
Like when we have to
So-
add chemicals into like a swimming pool,
Mhm.
you measure that based on pH, right?
Right.
So you're wanting to make sure it's got less acid in it to kill the germs or whatever, or,
I'm kind of thinking it's, I think chlorine is acting as a base, proton acceptor.
yes, and that's what's raising the pH to
Right.
where you want it to be, since you're adding more
Right.
base.
Yeah, yeah.
Yeah, you go take care of your pool.
Boom.
But you, but you could have just as easily done the pOH, you know. So this just kind of steps you through. Notice that in each of these cases, and if you're like, I could go backwards too. You know, we're just kind of going across the board. Like, do you see where these superscripts add up? You know, the powers of 10 add up to be negative 14. Does that make sense? Okay, so like you stop at any one point, and if you're 25 degrees Celsius, the molar concentration of your H plus times the molar concentration of OH minus should be equal to 1 times 10 to the minus 14th, essentially. 1.008 times 10 minus 14. So that's why you're kind of seeing that when you step through them. And you're going to use that to your advantage to work problems. Okay. What else we got? I like these problems. So these are just kind of some household things. These are kind of fun. You know, blue means basic, pink means acidic. Actually, I think that's consistent with, there's this paper called litmus paper? I don't know. It's paper that has a chemical on it. And blue, basic. Yeah, so if you have pink litmus paper, you can check for basicity. And if you are checking for something that's acidic, you need to have the pink paper, and it will turn, no. So blue, so you have pink for basic, and you have blue for acidic.
Question I like.
Wouldn't it just be white, they could turn either color?
Well, there's definitely paper that's more complicated than the whole pink blue. There's like, and we've got some in the lab that, I think I'll bring it out for Thursday. It turns different colors depending upon what pH it is.
I think we have that at work for our sanitizing solution.
Okay.
For cleaning pans and stuff, you gotta check it to see what color the paper turns.
Exactly. And is there more than one color it can
Yeah,
turn?
and it's got a little guide on there and how
Yeah.
bright or dark it needs to be.
Yeah, that's exactly what I'm talking about.
So that's kind of cool.
Yeah, that is very cool. So, if I circle the 25 degrees Celsius one, it's the one we're dealing with, okay? But you can see that if it gets warmer, then what happens to your KW? Does it increase or decrease?
Increase.
It increases. So if it increases, does that favor the products or the reactants? Because KW is just another equilibrium constant. Products, yep. So your products are to ionize. We're talking about ionization here, so yep. So that's kind of interesting. And as it gets cold, it's almost like they're cold and they, but trying to think, this goes, my mind's a little fuzzy, but just in the previous unit we talked about, this temperature dependency would have to do whether it's endothermic or
Yeah.
exothermic.
That's what I was just gonna ask, so that means it's endothermic, if the heat is on the side of products, that would be endothermic.
It's,
Excellent.
Is it- as you add heat, you form more, I'm thinking endo.
That's what I'm thinking, endo's on the
Yeah.
side of the.
Yeah, because you're
product.
adding heat and because you're getting more of your H plus and your OH minus. And it's a push.
Yeah.
I'm thinking it's endothermic, yeah. Exothermic would be, if it would be on the product side, if you add more heat, then you're gonna push it back to
It's-
the reactants.
This would
So it'd
have
be less
a
ionization.
positive delta H,
Yeah,
so it'd be-
endothermic. I'm thinking endo. Yeah, if we go back to the unit 3 and kind of talk about the temperature dependency and the trend in Ks.
Maybe I didn't understand the question, because I know which side is which, so yeah.
Yeah, so, yep, so I'm kind of thinking heat or energy, because as we're heating it up, we're getting more of this, as you can see by the, yeah.
Oh, I had it backwards, I thought it'd be the other way.
Okay, so-
Yeah, because he was saying the other
He
way.
was saying it would be on the reactant side would be heat.
Cause the H2O
But-
is the product.
But
or
this is a
reactant.
delta H is positive, right?
For if he's added on that side, but
Yeah, I must have it backwards.
sorry, okay. So, we were wrong, Mike. But yeah, I think we're on the same page now. Actually, I think we do look at that coming up. No? Okay. All right. So let's do a few problems, shall we? I think these are fun. And like I said, we're going to step back from the whole weak acid, weak base, and we're going to go to strong acids and strong bases. Just because it's cleaner cut, we know what the molar concentration of hydrogen hydroxide ion should be. So we're supposed to knock out 4 things, and this is very common. I said 4 things. 4 things, we're supposed to come up with the hydrogen ion concentration, the hydroxide ion concentration, the pH, and the pOH. It's kind of, would this be true? If you know one, basically you know the other 3, I think. You know, I really do. So let's go with the first one, HCl, strong acid, one-way arrow. In this case, it's just monoprotic. So, you know, you got 0.1 molar HCl, it's going to ionize completely. So we know the answer to one of our things. The molar concentration of hydrogen ion is going to be 0.1 molar. That's it. You can use that as a starting point, I would. You know, so if that's the case, now we're going to go ahead and grab our calculator. And I can't remember which order I do this, but if you take your calculator and take log of 0.10 times -1, what do you get? You get 1, right? Yep. So now here's where you get 1. Here's where, and I've been a stickler about rounding, and I'm still a stickler. I think we dealt with logs before. Logs and calculation, rounding gets a little interesting. After you apply the log function like we did here, we show significant figures past the decimal. Okay? So honestly, we had 2 sig figs in our molarity. To show 2 sig figs in our pH, we do this. Okay? All right, very good. Well, that's 2 out of 4. Now we can do it a few different ways. I can't remember which way I did it. I probably would go for the pOH, don't you think? So it's 14 minus the pH would give you the pOH. See if that's what I did. Yep. Added together for a dilute solution like this, that pH plus pOH is going to be 14.00. Rearrange it, then pOH is equal to 14.00 minus the pH. And you guys told me 1.00 for that. So I can do that in my head. Okay, 14.00 minus 1.00, of course, is 13.00. And this is the one we did right here, right? Yep. So then the last thing, and this finally gets a little more interesting or whatever, we need to kind of convert that pOH back to the hydroxide ion concentration. And we said to do that, you take 10 raised to the negative pOH. So find 10 raised to the, however you're going to do it on your calculators. 10 raised to the, mine says caret, negative 13.00. And what'd you get?
1 times 10 to the negative 13.
Very good. 1 times 10 to the minus 13th. Perfect. And now we're going to kind of backtrack, and we're going to pick up our 2 significant figures that we had in our kind of 13.00. Our 2 sig figs here now is going to be right here in the 1.0 times 10 to the minus 13th molar. So that's the hydroxide ion. So that's all 4 quantities. I think that I'm remembering now my slides. I think now I do the other approach. Let's see. The other approach would be once we have the hydroxide ion hydrogen ion concentration, we could go for the hydroxide ion concentration, recognizing this, that multiplied by each other, they have to be equal to that Kw, which with just 2 sig figs is 1.0 times 10 to the minus 14. So we can rearrange this, solving for the hydroxide ion. The hydroxide ion then is equal to Kw, which is 1.0 times 10 to the minus 14, divided by your hydrogen ion concentration, which we said that was 0.10. So then your hydroxide ion concentration is 1.0 times 10 to the minus 14th divided by 0.10. I can almost do that in my head. Okay, so your hydroxide ion concentration is 1.0 times 10 to the minus 13th moles per liter. Every once in a while, I'll do an alternate approach and I'll get a slightly different answer. So either one would be fine. So that's the third of 4 quantities, and then in this approach, we still have to knock out the pOH, which if you put this number, let's see, so we're gonna take the log of 1.0 times 10 to the minus 13th, log base 10 of that, times minus 1. And rounding to, or giving it two digits after the decimal, that gives you 13.00. So again, this, I think any of the 4 quantities you can backtrack to get your other thing. Okay? So let's take a look at the other example. And this one is a strong base. So you can tell it's strong if somebody gives you this information. I don't know if barium hydroxide is strong or weak. Well, somebody gave this to you and they showed you the one-way arrow. It's strong. Ionizes completely. So do you guys buy this? If we have a 0.0025 molar solution of barium hydroxide, in fact, we get 2 hydroxides for every formula unit of barium hydroxide, what's the molar concentration of hydroxide ion? It's not 0.0025.
You have to multiply it out with the stoichiometry.
Stoichiometry, yep. So what would be the hydroxide ion concentration? 0.0050, yep, just double, exactly. So that's the first of 4. That's where I would start. Just like you said, from stoichiometry. Now I'm getting a little, this is Chem 2, and you know, technically I guess I could show a stoichiometric calculation to do that, but actually if in this case you just want to jump right to that conclusion, I'm fine with that. So there we go, there's 1 of 4. There's the molar concentration of your hydroxide ion. I'd probably go pOH next, does that sound okay? So for the pOH, we're gonna take log of 0.0050 times minus 1. Bless you. Finally we get something, a number that's a little more interesting. To show 2 significant figures, because we had 2 significant figures in our molarity, we're going to actually show 2 digits after the decimal in our log. So 2.30 is our pOH. Yay! So that's 2 of 4. Now we're ready to, we got to turn our attention to the hydrogen ion or the pH. Can't remember what I do next. Either one's fine. I'd probably go for the pH next. Okay, I think that's what I do here. So in the same solution, the pH plus the pOH is 14.00 at 25 degrees Celsius. Rearrange for the pH. Of course, that means the pH is equal to 14.00 minus the pOH. So now we're ready to substitute in. And you wouldn't have to show all of this work if you didn't want to. You could go, but you do need to show at least this work. The pH then would be equal to 14.00 minus 2.30. Which I can't do in my head. I got 11.70 is the pH. If we did it this way, now we're ready to go ahead and kind of backtrack our pH to our hydrogen ion concentration. This is where we take 10 raised to the negative pH. So 10 raised to the negative 11.70, giving it 2 significant figures, because that's how many I got after the decimal there in that pH. I get 2.0 times 10 to the minus 12 moles per liter. And that's the hydrogen ion concentration. I guess we could do a check, couldn't you? You could take this hydrogen ion times the hydroxide ion, see if you get 1 times 10 to the minus 14th. The other approach would look like this. If instead of going for the pH, we went for the hydrogen ion concentration, we would recognize that your hydrogen ion concentration times your hydroxide ion concentration in dilute aqueous solutions is 1.0 times 10 to the minus 14 to 25 Celsius. Rearranging for the hydrogen ion, looks like this. It's that Kw, which is 1.0 times 10 to the minus 14, divided by your hydroxide ion, which we knew was that 0.0050 moles per liter. So your hydrogen ion then would be equal to 1.0 times 10 to the minus 14 divided by the molar concentration for hydroxide ion, 0.0050. This is kind of fun where you don't have to worry about units. Yeah, I mean, it's kind of the whole weird. So 2 sig figs, I get 2.0 times 10 to the minus 12 moles per liter. So that's the third of 4 quantities with this approach. The last quantity would be to take the hydrogen ion to knock out the pH. So we're going to take the log of this number times minus 1. So the log of 2.0 times 10 to the minus 12 times minus 1 will give us our pH. This is just something I'm sure you picked up or will pick up, but if you're in base 10 and you have something in scientific notation, ballpark, this is how this works. Ballpark is going to be kind of whatever this exponent is. It's going to be 12-ish. Okay? So when you apply the P function, you get 11.70. Remember that once we apply the P, when we take the log of something, our sig figs are shown after the decimal. That's showing 2 decimals. Isn't this a little different than we had on the previous one? Wasn't the previous approach, what was the pH? Was it 11.7? The same?
14 minus 2.3.
Oh. But sometimes they're a little different. Okay, very good. Dun, dun, dun. Does that bring us to an assignment slide? I guess not. So acidic solutions are one in which the scales kind of tip. Okay, and I like the idea of tipping scales because in dilute aqueous solutions, as the hydrogen ion increases, the hydroxide ion decreases. Okay, neutral, and then hydroxide increases and hydrogen ion decreases. I think that's kind of fun. So here's a bunch of more things about acidic solutions. The hydrogen ion will be greater than neutral, greater than 10 to the negative 7 moles per liter. Hydroxide ion will be less. Your pH will be low, and your pOH will be high. Don't blame me, okay? So that's just kind of how it works. And then we could look at an analogous slide for basic solutions. By definition, with regard to an aqueous solution anyway, we call it basic if the scales have tipped and your hydroxide ion concentration is more than your hydrogen ion concentration. So that has consequences. That means that your hydroxide ion concentration is going to exceed that tipping point, 1 times 10 minus 7. Your pOH will be low and your pH will be high. So however you need to kind of remember all that. Think a big picture, probably a good idea. Neutral solutions, they're equal. I just think that's cool. If your water is neutral, you're like, well, there's no hydrogen ion. Well, yeah, autoionization, you know, and the molar concentration of both the hydrogen ion and the hydroxide ion will be 1 times 10 to the minus 7th moles per liter as long as it's 25 degrees Celsius. And your pH and your pOH are both 7. So we'll be dealing more with pKa's, okay, pKa's and pKb's. All a pKa is you take the Ka and you apply the P function, which means take the log base 10 of that times minus 1. That's it. But my thing up here is there'll be times when you need to be able to go back and forth between a pKa and a Ka, and here's how you do it. So let's take a quick look at these. I think they're fun. 16, 9, and 10. They look like this. The fact I said I think they're fun means I haven't looked at them this year. I'm sure they are. Okay. So here's all the hints I have about the first one. Again, get those 4 quantities. Now you got lots of practice. We have, what, 5 different solutions? Okay. But you don't need the pH and the pOH. All you need is the hydrogen ion concentration, or the hydronium, same thing, and the hydroxide ion concentration. There's your hints for that one. And then here's this one. I think they're kind of similar. What's the pH? So you only need 1 quantity. And in each of these cases, we're going to kind of be switching gears after part 2, but these are all strong acids or strong bases, 100% ionization. Okay, so you don't have to like think too hard, hopefully, what product's going to be formed. Okay, any questions, Mike?
So that, the chemical equation you have written right there, is that the chemical equation for A, B, and C?
I think it's just for D, actually.
Or for D, okay,
Yeah, just for D, yeah. And it's like the one that we did just a little bit ago about barium
Yeah.
oxide, yeah. So, yep, and there are definitely choices how to get to this, the information that you're supposed to get to. It's good practice. Very good. Well, we'll see you maybe on the hill tonight.
You said that's 9:45?
Well, I think I told Mike I'd start looking at 9:40, so I'm gonna have my gear all set up and my, the way